Okay, welcome back, and today we're going to continue on with the hypothesis testing, and today we're going to talk about the p-value method. So we're going to use the same example that we used before. So again, we're going to set up a hypothesis, and this time we're going to use the p-value method. Okay. So again, we're looking at these computer components, and we're looking at the time between failures. And so last time we knew, based on the claim, that the claim was the alternative hypothesis because of the way it's framed. So this would be 520 hours versus mu is less than or equal to 520 hours. And so this is our claim. Okay, and we're doing a right-tailed test. Okay, so now the p-value method deals with something called p-value. What is p-value? Well, let's write down the information from the sample data, okay? So this is where we're going to write down the sample data again. So again, we're assuming the null is true. This is our claim, and we're going to test this claim using a right-tailed test. So now, the data we given, n was 100. We assumed that sigma was equal to 23. And we had x bar, and we said, well, what's that? We assumed x bar was, let's say x bar was equal to 5, what was it? Equal to 522? Or no, 533. If I remember right. So 533. And so last time we used the traditional method, which was calculating a z-score, right, the test statistic, z star, and then figuring out what the critical value was, and then comparing the two and seeing if the critical or if the test statistic falls within the rejection region. Okay. Now we're going to use the p-value method. Okay. So again, we're going to assume that sigma is known, right? So sigma is known. That's the assumption right now. Okay, so sigma is known, and here we're given sigma is 23, and this is 23 hours. And so now, what the p-value method works is we're going to find the probability of getting the sample statistic that we got, or a sample statistic that's more extreme. And how do we know what's more extreme? It's going to be in the direction of the tail. Always the direction of the tail. So again, the alternative hypothesis tells us the test. Okay? So when we calculate this probability, it's going to be a right-tailed test. So what we're going to do is we're going to calculate the p-value, and the p-value by definition is always the probability of getting a test statistic equal to or more extreme of the value that we got from the sample. Okay? So in other words, this is the probability that we get a sample statistic, x bar, equal to or greater than 533. So equal to or greater than 533. And once again, in order to find this probability, we need the distribution of x bar. And of course, from last time, we know the distribution of x bar is normal with a mean of mu. What mu? What we're assuming to be true, 520. And a standard deviation of sigma divided by the square root of n, which is equal to 23 divided by the square root of 100. Okay? And so once again, we need to know this in order to calculate this probability. So now that we know the distribution of x bar, and of course the sample size gives it to us because of the central limit theorem. Okay? And so now, what function in our calculator can we use to figure out a probability given a normal distribution? Normal CDF. So we're going to use normal CDF. And so with normal CDF, we need to put in the lower bound, upper bound, mean, and standard deviation. So the lower bound in this case, what's the lower bound for this range? Well, it's greater than or equal to, so it's going to be 533. So that's the lower bound. And then the upper bound in this case is going to be 10 to the 99th power. So we want to make it really big, just like we talked about before. So 10 to the 99th power, followed by the mean. What mean are we going to put in? 520. That's under the null. And then followed by the standard deviation of x bar, which is 23 divided by the square root of 100. So, which is going to be 2.3 in this case. And then, so what do we get? Well, let's figure it out. So let's go to our calculator. And let's calculate what the probability is. Okay, so the mean is, what's the mean? Mean is 520. Standard deviation is 2.3. And we want, let's see here. We want above 533. And basically we get pretty much 0. Because it's such a high, again, this makes sense. Let me see if I can get the decimal places here. It says 0. Let me see if I can get another one. Okay, so here we go. We're going to do 520, 2.3. And I want 533. And yeah, it gives me 0. So it must be a really small p-value. And which I kind of figure it's going to be really, really small because of how many standard deviations above the mean we are. We're over almost 6 standard deviations above the mean. So if you remember the empirical rule, it's going to be a very small probability. So this is going to be equal to approximately 0. Okay. In fact, it'll probably be like 0.0000 1 or something like that. So a really small p-value. Okay. I don't have my calculator with me, but just put it in the norm CDF. It'll give you the value. I'm using the computer, so all they do is say 0. So it's got to be really small. So just keep that in mind. So this is not the real p-value, but it's going to be really small. So now, with this p-value, now what are we going to compare this p-value to? Well, in the traditional method, we compared our test statistic, which was based on the sample data, with the critical value, which was based on alpha. So in this case, we're going to compare our p-value, which is a probability, right? The probability of getting a sample statistic as extreme or more extreme than what we got, right, in the direction of the tail, right? So we're going to compare that probability with another probability, the probability of making a type 1 error, which is alpha. So we're going to compare p-value always to alpha. And here's the general rule. The general rule is this. If p-value is less than alpha, we reject the null. So let me say that again. If p-value is less than alpha, we reject the null. Okay? So keep that in mind. So now, in this case, again, we said that alpha was 0.05. Okay? So in this case here, p-value, which is equal to 0.00001, let's say, is definitely less than alpha, which is equal to 0.05. And so therefore, we will reject the null, right? So that's the mathematical symbol for therefore, a triangle of dots. So again, we're going to calculate our p-value based on the sample statistic. And then we're going to use that p-value compared to alpha. And if p-value is less than alpha, we reject the null. That's it. That's the test. That's the p-value method. Okay? So now, so far we're just talking about whether we reject the null or fail to reject the null. Okay? So that's all we're concerned with at this point. Okay? So now let's expound this on all the different tests. Okay? So again, now let me show you the p-value when you do a two-tailed test, a right-tailed test, or a left-tailed test. So let me look at this. Okay. Here's the general rule is still the same. Okay. Remember, as long as you follow the general rule for the p-value method, you'll always get the correct answer. If p-value, so remember, whatever your p-value turns out to be, whatever your p-value is, if p-value is less than alpha, you reject the null. That's the general rule. That's all you have to remember. Now, how you calculate p-value is different depending on the test. Okay? So if I do a right tail, then your p-value is going to equal to the probability that your test statistic, x bar in this case, right, your sample mean, is greater than or equal to whatever the value is that you got, okay, which would be whatever your test statistic is, right? Okay. Okay, makes sense? Okay, now, if it's a left tail, then p-value is equal to the probability that your test statistic, x bar, your sample statistic, is less than or equal to whatever the value turns out to be from your sample. Okay? So in the right tail, the probability is going to be greater than or equal to whatever the value is you got from your x bar, whatever that x bar value is. Okay? If it's a left tail test, then it's going to be the probability of your statistic, your x bar, your sample mean, is less than or equal to whatever you got with the sample. Now with the two-tail test, this is where you have to be careful, because you have two tails. The two-tail test, your p-value is going to be double, right? Because if you're calculating, let's say you get a statistic, right? Let's get you get your sample mean. Whatever that sample mean is, you're going to calculate the probability of being either greater than or less than, okay? But remember, you have two tails. So you have to calculate the probability of being greater than some value and also being less than the value. Okay, but you're only calculating one tail. Okay, so what you're going to do is you're going to calculate the probability of being in that tail, right? Because your critical value, your sample mean is either going to be over by this tail or it's going to be over by this tail, okay? So whatever it is, you're going to find the value or the probability of being as extreme or less extreme, but then once you find this probability, it's going to be equal to this probability as well because it's symmetric, right? Because we're assuming a normal distribution, right? That's what we're banking on. So what you're going to do is you got to take this probability and double it because it's the same as this probability. So you're going to take this plus this, which is going to be the same as taking 2 times the probability. So in other words, let me write it this way. Okay. So whatever your probability is that you end up figuring out, you have to double it. Okay, that's with the two-tailed test. Okay. So just be aware of that. Okay. If you use the formulas and you're calculating, or the calculator to calculate your p-value, and you're using normal CDF, you got to make sure you double it if you're doing a two-tailed test. Okay. Now, once we get into the actual test, I'm going to show you some functions on the calculator that will actually do the tests, and you don't have to worry about doubling the p-value. The calculator will give you the correct p-value automatically. All you have to do is tell the calculator what test you're doing. Okay. So we'll get there. Okay, so this is the p-value method. So it's really straightforward. Right-tailed test, you're going to find the probability of being greater than or equal to your sample mean. If you're doing a left-tailed test, you're going to find the probability of being less than or equal to your sample mean. If it's a two-tailed test, you're going to either find the probability of being greater than, or you're going to find the probability of being less than your sample mean, and then double it. Okay, that's really what it is. But remember, the general rule is always the same. If your p-value is less than alpha, you reject the null. Otherwise, you fail to reject the null. Okay? And that's it. Now, let me show you the connection between the p-value method and the traditional method. Because it doesn't matter which method you use, you should always get the same result in your test. And that's why in my class, and typically on any exam, I won't care what test you perform, unless I specifically say, hey, perform this test, or hey, perform this test. But if I don't tell you to perform which test, then use whatever test you want to use. Typically, the p-value method is the test that I always prefer. It's the most common method, but you can also use the traditional method. The point is, it doesn't matter which test you use, you should always get the same result. If you don't, then you did one of the tests incorrectly. Okay, so keep that in mind. So now let me draw the curve again. So let's draw this curve. And I'm just going to show you with one test, with one tail. So here is our distribution. So here's 0, so let's say this is our test. And let's say, and I'm going to exaggerate this so I can show you. Okay? So let's say this is the rejection region. Okay? So this is the rejection region. And I'm going to color this in. Okay, and what I'm going to do is I'm going to label the critical value here. And this is going to be, I'm going to call this Z alpha, okay, or negative Z alpha. Okay, so let's say we're doing a left-tailed test, and this is going to be the rejection region. So let me label that. So just like before. Okay, so here's the rejection region, and here's my critical value. So here's the idea. So now, with the traditional method, what did we say? If my Z star falls within the rejection region, so in this case, it's less than or equal to, right? Less than or equal to what? Oh, hold on a second. Let me double check something here. I want to make sure. Greater than. So let's use less than. It doesn't. Let's just use less than or be consistent. So it's less than. So in this case, we're going to reject if it's less than our alpha level. Okay, I know I used less than or equal to, but let's be consistent with the textbook and let's use less than. So if it falls within the rejection region, so in this case we're going to use less than our negative z alpha. Okay, since it's a left tail test, we're going to reject if it's less than this critical value. Okay, so that means if my test statistic falls, let's say right here, and let's say this is my z star. So in this case, using the traditional method, my test statistic is less than my critical value. So therefore, right, therefore, we reject the null. Okay? So now, what about the p-value method? Well, remember, what is the p-value method? Well, let's think about that. How did we get this critical value? We used alpha, right? What is alpha? Remember, this is a left tail test, right? So what's alpha? Alpha is the area in the left tail. It's the area in the rejection region, right? So that means this area here is alpha, right? Now, what do we compare alpha to? We compare alpha to the p-value. Well, what is p-value? Well, remember this definition. Always remember this definition of p-value. It's the probability of being as extreme or more extreme than the test statistic, or your sample mean, right? Or your sample statistic, right? Well, remember, way back in chapter 3, we showed that the probability, for example, let's use this, that x bar is less than or equal to, right? The probability that x bar is less than or equal to some value, right? And let's call it x bar here, right? We saw that if we have a normal distribution, we could transform it into a z-score that's equivalent, right? We talked about equivalent z-scores. We could calculate an equivalent z-score that matches up with this, that corresponds with this sample statistic. So we always said that, hey, this probability will always be equal to the corresponding z-score. So in this case, x bar turns out to be your z star. Your actual value turns out to be whatever it is. So it'll be x bar minus mu naught over the sigma divided by the square root of n. So whatever that value turns out to be. So these two probabilities are the same. So p-value is the same as the area, right? So this p-value is the same as the area to the left of what? Your z star. So in other words, p-value is the area to the left of my critical value. Or not my critical value, I'm sorry, of my z star, my test statistic. So now, I'm going to reject if p-value, right, if p-value is less than alpha, I think that one should be, I'll have to look that up, but I'm going to put the equal sign in there. If p-value is less than alpha, then what should we do? Reject the null. So now, Let's look at this. The traditional method says, in this case for the left-tailed test, if my test statistic falls within the rejection region, in other words, if my test statistic is less than or equal to my critical value, then we reject the null. But what does that mean? If my test statistic is inside the rejection region, well, what's the area to the left? Well, it's p-value. Well, if my test statistic is inside the rejection region, my p-value will automatically be less than what? Alpha. So if I do the traditional method and I reject, then the p-value method should also reject automatically because it's the same test. That's the thing. You're doing the exact same test. It's two sides of the same coin. It's just a different method of doing the test. So that's why if you do the traditional method, you should always get the same result if you also do the p-value method. Okay? Because from the diagram you can see it's the exact same test. Okay? So now that's the p-value method and how we relate the p-value method to the traditional method. It's the same test. You should always get the same result regardless of which method you use. So again, just keep that in mind, and next time we're actually now going to start doing the 7 steps. So we're going to do the 7 steps, and I'm going to do the 7 steps with the problem both ways, using the p-value method and the traditional method, and then we'll go on from there, and we'll just keep doing examples for the rest of the chapter. And then what we'll do is, after we're done with the means, we'll start talking about, hey, what about hypothesis testing involving claims about population proportions? Or actually before that, we'll talk about what about if we don't know sigma? Okay, then we're going to have to talk about the t-distribution, just like we did in chapter 8. Okay, so anyway, that's it, and hope you enjoyed it, hope it made sense, and let me know if you have any questions. Take care.